So a note on series. Sometimes it's not too bad to start taking derivatives and then find the coefficients. Other times it's a function we already know, like we're thoroughly familiar with the cosine of x. And it's easier in this case to take the cosine of x, the series, and substitute in for x squared and then multiply by 7 and then see what the coefficients are for each power of x. And in this case, for example, C2 refers to the coefficient that goes with x squared. So you got to use your judgment as whether it's going to be easier to take derivatives, or if you recognize the function. I find it easier if I already know the function, I know its series, just manipulate it rather than take repeated derivatives. Because sometimes, like we saw in the last class, those repeated derivatives can be quite the mess. All right, so one thing I promised before we got into power series is that they would allow us to evaluate series that we knew converge, but we didn't know to what. So there's a couple of examples at the end here that deal with that. So we're gonna pick on these and figure out, based on stuff we know, what this series converges to. So let's give it a try. So let's copy this into my whiteboard and we will manipulate it. All right, this was number 10 in the homework. So first thing I see is the n factorial, and I'm thinking, oh, this is something like e to the x. So right away, I start comparing this to the series for e to the x. All right, so I have to make this look like x to the n. So the denominator looks good. So now I just need to mess around with the numerator to make this look like that. So the 4 to the n minus 3, I think I'll reconsider that, reversing properties of exponents, as 4 to the n divided by 4 to the third. Right? Because when we have the same base and we're dividing, we subtract those exponents. The reason I like that is because now my numerator looks more like e to the x. Now we do have that -1 hanging out to the power n, but fortunately that has the same power as this. Okay, so right now, switch color, what I think I can do is take that numerator and rewrite it as -4 to the n divided by 4 to the third. Now we also have that n factorial hanging out, and all of this is inside the sum. So I'm just trying to manipulate what I have to look like something I know. Now, n is our variable here, so 4 to the power of 3 is just a constant. I can pull that out. So now I'm going to reconsider it as 1 over 4 to the third times the sum as n goes from 0 to infinity of -4 to the n over n factorial. And now it looks like the power series for e to the x, where x is -4. So my guess is that this converges. So based on what I have above here, this right here should be e to the power -4, and then I have a multiple of 1 over 4 to the third. And so now I'm just going to test that computationally to see if they match. Now I know we have that system that tells us if we're right or wrong, so just remember though, on a test, we don't have that system. So we want to find ways to check ourselves before we hit that button to check our answer. So I whipped out GeoGebra somewhere here. All right, so GeoGebra, please sum for me sequence with some room to calculate. My expression is, oops, too far. Parentheses. I'm going to write it the way it originally was in case I messed up any of my conversions there. So, I hate when you do that to me. Fine, we'll get rid of everything here. On some computers, GeoGebra is kind of glitchy on me, and others it's not. This computer, it always is. All right, so -1 raised to the n. What was next? Times 4 raised to the power n minus 3 divided by n factorial. Does that look right? All right. and then that's inside the sequence. So then I want a comma, n is my variable, comma, start at 0, and let's go out for the first 100 terms. GeoGebra can handle that. And enter, and the computer says it's 0.000286. So I believe that should be approximately the value, let's see, what did I figure? E raised to the power -4 divided by 4 to the third. And man, look at that. 15 decimal places of accuracy at 100 terms. I wonder if we can back off. Let's see, let's back off to 10 terms, see how close we get. 10 terms, ooh, is not close enough. Yeah. All right, how about 50 terms? 50 terms nails 15, yeah. And then do we have a way to estimate the error involved here? The alternating series test, right? The next term should give us a bound on the error, so we could check that out. Now we went out to 50. I don't know how GeoGebra can calculate this. So the next term would be n equals 51, and then -3 over n factorial, ignoring the sign. So the alternating series test says the next term in line is bigger than your error. So let's calculate that. Let's see, where do I calculate it? Over here. So I think my error is 4 raised to the power 51 minus 3, which is what, 48? Divided by 51 factorial, which is an incredibly big number. And yeah, GeoGebra was like, yeah, I only have 15 decimal places, so it's 0 for me. Okay, interesting. I wonder if we could go out to 20. 20, and then this would be what? 21 minus 3 would be 18. I can calculate that. So let's see, if we go out here to 20, then it says I have 1, 2, 3, 4, 5, 6, 7, at least 8 decimal places of accuracy. And if we look at these two series, we definitely have 8 decimal places of accuracy. So the alternating series test is right on in terms of about how accurate we are, which is pretty cool. 37 zeros, nice. Wow, I don't know when we'd ever need that in life, but heck, we can get it if we want it. All right, well, no, actually I do know when we would need something like that. So do you guys know that we made a device that can measure gravity waves? Yeah, and it's crazy. It's this huge underground tunnel, and they have this laser pointing miles through the tunnel. And if the laser moves a little bit, they can tell whether it's an earth tremor or a gravity wave. And the amount it moves is like about that small. It's amazing, it's like nanotech small. It's nuts. And we can measure this. And they're working on a new one that's going to be more accurate. Well, about the same accuracy. I think it's either going to be in India or France. And then they're working on another one that's going to be based on satellites out in space, which is nuts. Anyway, so yeah, sometimes we do need to be that accurate, but not very often. All right, let's do another one. So the next one was kind of cool too. So the next one was a little more general. This one didn't give us a particular value of x. It just says, hey, this is a power series. What power series is it like? And, well, right away, I'm thinking, hey, this looks like e to the x. Let me get a new screen and clip it. Oh, clip it. There you go. All right. So now we just have to manipulate it until it looks like e to the x. So kind of similar to last time. I'm going to say, just look at the numerator for now, because this is something like e to the x. And there might be something else outside. All right, so x to the 5n minus 4 can be rewritten as x to the 5n over x to the 4th, right? What about the x to the 5n? How would I rewrite that? Yeah, we could say, hey, this is x to the 5 to the n. In which case we now have something to the power n, which is what e does. So it looks to me that this series is probably e to the power x to the fifth divided by x to the fourth. And if I just double check on that, I'm going to have a 1 over x to the fourth outside my sum. E's sum, n goes from 0 to infinity, of e to some power over n factorial. And we've just broken it down. Oh, what am I doing? That's not the way it looks. I wrote the e in the wrong spot. That was bizarre. Come on. E's power goes here to the n over n factorial. There we go. So whatever power I have for e has to go here. All right. So I think we got a series there. So we think this is e to the power. Now, sometimes people will write this thing without parentheses, but I do think they're necessary because exponents aren't commutative or distributive. No. What's the other one? Associative. You can't change the order of the parentheses. You get a totally different result. So the parentheses go there. Oh, yeah, you all right? Okay. Yeah, so what can I do to check that? Well, I guess I could graph a few of these and see. So I think for that, I would like the Desmos grapher. Means I have to leave this page, open a new tab. Desmos sum grapher is what I want. So what I want to do, ooh, can I do that here? Have I tried this before? Now this is set up to do regular series. I think I need to hit GeoGebra out for this one. All right, let's see. I want to sum the sequence. And my sequence is, trying to remember, it is what? X to the power 5x minus 4 all over n factorial, right? Oops, oh, I got x's and n all mixed up there. N. All right, do I have the right one now? Okay, and that's going to go with n from 0 to, let's go with the first 10 terms. Whoa, that's cool. All right, and then I think that should be the same in some interval to e raised to the power x to the fifth divided by x to the fourth. And it looks like it's in this interval right here that I've got to match. Or, oh no, that interval too over there. Yeah, let's shrink this down. Oh wow, look at that. That's wicked cool. That's a crazy looking function. Does it have, oh, it's asymptotic there in the middle. I see. Yeah, so the functions sit right on top of each other, right around 0. Yeah, because 0 is the center here. Yeah. But the function doesn't exist at 0 because we're dividing by x to the fourth. And the series doesn't exist there either. Or no, I bet actually the series is going to have a max there because it is a polynomial. So somewhere, which one is it? The blue one is going to go down and come up. Oh, wow, it's way up there. Where are you? Well, it's got to, because this series has no x's in the denominator, right? So it's defined at x equals 0, even though the function isn't, because we stopped, right? We didn't calculate the whole series because we can't, because we're humans. So somewhere it's got to peak. Come on, where are you? I guess I could just ask GeoGebra for the max. It'll give it to me. I swear it's got a peak. It is a polynomial, not a rational function. All right, I give up. It's there somewhere. All right, I'm almost ready to give up. Where the heck are you? You're making me look like a liar. I swear I'm not lying this time. I know sometimes I make shit up, but I'm not this time. Oh, Oh, you can't do, I maxed out GeoGebra. When it, yeah, GeoGebra said, sorry, I'm out of steam, man. You can't use any more computational power. Wolfram Alpha, I bet, would do it. We got a couple minutes. I'm curious. I know Clint doesn't believe me here. He says I'm full of it. So sum, let's see, I am summing x raised to the power 5n minus 4 divided by n factorial. And I'm only going to go out 10 terms. Load this up, and it should give me a graph. Oh, come on, show me the peak. Oh, here, okay, so here you can see it looks flat when they go up to 10 to the 30th. Yeah, so they zoomed out far enough. So we had to get out to 10 to the 30th, or probably a little less than that, to see it. And it won't let me change the range, unfortunately. Will it? Oh, if I log in, they probably will. Anyway, okay. It does have a max. It's less than 10 to the 30th. GeoGebra couldn't handle it. All right. What's that? You just plug in 0. Does the max have to happen at 0? I guess I would have to take the first derivative to prove that. Oh yeah, you can kind of see it when you look at the series. So let's see, they show it here. So here's my series. Let me zoom up a little bit. Oops, too far. Oh, stop it. Come on, just give me the whole thing. So if I take the first derivative of this and set it equal to 0, oh, interesting, they put an x to the 4th in the bottom. Fascinating. Oh, did I lie? Oh yeah, the first term or the second term. Let's see, if n equals 0. Oh yeah, then they factored. That's a weird display of this. Oh, they're not in order. I see. Yeah, that when n is 0, the first term is x to the negative 4th. So I lied. This isn't a polynomial because of that shift in the top. It is actually a rational function. Darn, I did lie. Okay. So this picture is somehow deceiving. It does have a vertical asymptote there. We just can't see it. All right. Learn something new every day. It's good for you. Okay. Next. We are going to calculate a new series we haven't done before. And we are going to find a series for f of x equals the square root of x. And I think we're going to center it at 1. Centered at 1. Now, here's my problem with series that aren't centered at 0. I'm so used to finding series that centered at 0 is I accidentally start writing powers of x later. So we got to make a big note to remind ourselves that we want powers of x minus 1, not powers of x later after we calculate those coefficients. And there's a classic mistake lots of people make because so often we do series centered at 0. That we just want our coefficients to go with powers of x. But not this time, because of the centers at 1, those have to be our powers of x. All right, so we need to set up our table for Taylor series and start taking derivatives. And I think we can fit that on here. So we need a column for n, then the function or the nth derivative evaluated at 1, and then we're going to take that value and divide it by n factorial. Oh, I guess we need the derivatives first. Let's slide you guys over. All right. Okay, so n equals 0 we have to do first, and that's just the function itself, square root of x, and the square root of 1 is 1, and 0 factorial is also 1. All right, so then we view x as x squared of x as x to the 1/2, and the first derivative is going to be 1/2 x to the negative 1/2. And we could rewrite that as a square root, but since we got to take the derivative again, I don't think it's worth it. And then we plug in 1, and we get 1/2 divided by 1 factorial, which is still 1/2. And we take the next derivative. So what do we get next? For the second derivative, we get 1/2 times negative 1/2 times x to the negative 3/2. That look right? Okay, and we plug in 1, and we get negative 1/4. Oops. And then we have to divide that by 2 factorial, which is 2, so we get a negative 1/8. Let's do it again. Third derivative is going to be positive times negative, so it's going to be 1/2 times 1/2 times 3/2 times x to the 5/2. What's that? Negative 5/2. Thank you. I got too crazy getting rid of negatives. And so multiplying that together, I get what, 3/8. And we're going to have to divide that by 3 factorial, which is 3 times 2. So that was that 1/16 on a good day. Better write that down. 3/8 times 1/3 factorial. The 3's cancel. Yep, 1/16. So we've got the first 3 terms. Let's go for the 4th term because we can. See if I can shift all this stuff up. Catch enough of it? I think so. Perfect. What color are we on? Red. All right, 4th derivative. 1/2 times 1/2 times 3/2 times negative 5/2, and I'm quickly running out of room, x to the negative 7/2. 3 times 5 is 15/16, negative 15/16. Divided by 4 factorial. Four times 3 times 2 times 1. Let's see, the 3 goes into 15, leaving a 5 behind. That's about it, huh? So 16, 32, 64, 128. Is that where we're at now? So this is what, negative 5/128. Are there some patterns going on here too that we could pick out eventually? We'll come back to that. So I'm going to list out the series I think I have so far. Help me out if I mess this up. I think that the square root of x is approximately equal to, because we didn't calculate all the terms. So here's that first one again. It was 1. And then plus 1/2 times x minus 1. What's next? Minus 1/8 times x minus 1 squared, right? The 1/8 is in the n equals 2 row. Plus 1/16 x minus 1 cubed, and we have an extra one. Sorry, it was a minus, right? Minus 5/128 x minus 1 to the 5th. 4th, yes, right, 4th. That was the 4th step. We didn't get to the 5th one, but I bet I can predict the 5th one by looking at the 4th one. Oops. before I do that, I'm going to graph this to see if it looks okay. Okay, does that polynomial right there look like the square root function near x equals 1 is what I'm curious about. So I think I better get a new GeoGebra screen for this. I kind of maxed out that one. And hope it wants to use that other one. No, I don't. Let's go incognito. Whoa, did I just crash the computer? I'm about to, I think. Too much calculating, it says. All right, we don't really need this stuff. How do I get rid of it? Bye-bye. 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 Sometimes I feel guilty deleting that stuff, but we could always do it again, right? All right, so let's see. Help me out. It was 1, right? Plus 1/2 times x minus 1 minus 1/8 times x minus 1 squared plus, what was this one, 3/16? 1/16. Okay, plus 1/16 x minus 1 cubed. Oops, I missed the power. Cubed, there we go. And then minus 5 1/28. On the right track. X minus 1 raised to the 4th. And oh, we got that crazy scale, darn it. Let's see, how do I reset you? If I go here, 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 no, settings, aha. And we want to take a look as x goes from, let's say, 0 to 3, and y goes from 0 to 3, should be good. Close you. And just move this a little bit. Does that look like the square root? Let's see. SQRT of x. Hey, look at that. And double check. X equals 1 is my center. Oops. X equals 1. Yeah, I'm pretty tight at x equals 1, and then it starts to deviate either way. Okay. Now, we can't apply the ratio test to see what the bounds on this are yet because we don't have a formula for the coefficients. So that's kind of a problem. Might we be able to come up with a formula? Oh, maybe. Let's give it a try. Oops, it's always worth trying. Oh, it is there. Just hiding on me. Where's my notebook? Okay, so I was going to try. Come here. There you are. I was going to try and predict the next coefficient. Well, it looks like we're going to have, when n is 1, we have a 2 in the bottom. When n is 2, we have 2 2's in the bottom. When n is 3, we have 3 2's in the bottom. When n is 4, we have 4 2's in the bottom. So when n is 5, we're going to have 5 2's in the bottom. Okay, so we got that. And then, let's see, if we're at 2, let's see, 1 led to 1 in the top, 2 led to 1 in the top, 3 led to 3 in the top, 4 led to 5 in the top, 5 is going to lead to a 7 in the top. That one's a little bit trickier. So let's see. So I think, anyway, for n equals 5, the coefficient is going to look like this. It's going to be a, what sign are we on now? Positive? And then, let's see, we're going to have, I forgot, where was I? Oh, we got up to 5. So next we're going to have a 7. So if n is 5, we're going to have a 1 times 3 times 5 times 7 in the top. We're going to have a 2 to the 5th in the bottom. Oops, wrong way. That takes care of what the nth derivative is doing. And then I also have the n factorial to contend with also. So I'm also going to have a 5 factorial down there. And then the 6th one, that's going to bring us, what's the next numerator we're going to throw in there? A 9, right? Because of the way we're working with that 1/2 negative power. So we're going to have a 1 times 3 times 5 times 7 times 9. Now there are some multiples of 1 I'm leaving out. I don't know if that's important or not yet. It's going to alternate sign here. I'm going to have a 2 to the 6th in the bottom, and I'm going to have a 6 factorial. All right, so let's see. Here I have an odd number. right? And an odd number is always going to be something like 2n plus or minus something. Well, if I take 2 times 6, that's too big. 2 times 6 is what, 12? But if I take 3 away from that, I get 9. Does that work up here too? 5 times 2 is 10, minus 3 is 7. Yeah, that works. Okay, so it looks like for the nth one, let's see, when the power is even, it's negative. When the power is odd, it is, or when n is odd, it's positive. So I'm going to have a -1 to the power n plus 1, say. Could be an n minus 1. You can go either way. And then it's going to be a 1 times 3 times 5, odd numbers all the way up to 2n minus 3, divided by 2 to the n factorial. Those are my coefficients. That wasn't too bad. So we could try to apply the ratio test to this and see what happens. All right, so that's the nth term. Can we write the n plus 1th term? That would just be replacing each of these n's with an n plus 1, okay? And oh, what is x doing? That's just the coefficients. Back this way. Yeah, so the coefficient of x to the 4th is that. So it's just x to the n for each of those. So there's no, we don't lose any powers like sine and cosine do. So we're okay. All right, so ratio test, let's try it. Ratio test. All right, so the nth plus 1, we're going to ignore the sign because the absolute value. We'll have an x to the n times 1 times 3 times 5 all the way up to 3 times n plus 1, no, 2 times n plus 1 minus 3. That's my numerator, right? Yep. My denominator is going to be a 2 to the n plus 1 times n plus 1 factorial. And then we reciprocate that nth term we think we just found. So let's switch color. That's going to be a 2 to the n times n factorial over, oh, this was an x to the n plus 1, shouldn't it have been? Right there, because that's the n plus 1th term. And this is going to be the x to the n, 1 times 3, all the way up to 2n minus 3. And then close the absolute value. All right, cleaning this up. Well, the 2 to the n plus 1, 2 to the n goes into that twice. X to the n goes into x to the n plus 1 x times. N plus 1 factorial is really n plus 1 times n factorial. So the n factorial part goes away. And then let's see, what is this guy? If I clean this guy up right there, that's going to be a 2n plus 2 minus 3, which is 2n minus 1. And these are odd numbers, right? So what odd number is right before 2n minus 1? What odd number is right before? So an odd number, we have to subtract 2 to get there. It'd be 2n minus 3, right? Yeah, so right before this guy is a 2n minus 3. Point being, that's all of that stuff right there. So lots of stuff cancels here. I don't think I put this problem on a test. This is kind of nuts, huh? All right, so what's not canceled? Let's see, we have an absolute value. We have an x in the numerator. We have a 2n minus 1 in the numerator, but I think everything else was canceled, right? And the denominator, I think we just have a 2 times n plus 1. Yeah, I think we got that. And then we just need to take the limit of that as n gets big. That's an infinity for big. Well, x is a constant, so I can pull out the absolute value of x. The rest of this stuff is positive. What's happening to this chunk right there as n gets huge? It's going to 1, isn't it? Yeah. So I'm left with just the absolute value of x. Ratio test says that has to be less than 1. So I have a radius of 1, and I think we'll call it good there. We could check the endpoints, but then that's like this problem we got stuck on a few days ago that I still keep forgetting to go back to, and I'm pretty sure I'll get stuck again. So challenge, check the endpoints. I will too, and report back tomorrow. I better write that down or I'll forget. Put it in my special notebook here. Check endpoints. Oh, so what are our endpoints here, by the way? Because I just made a mistake up there on the screen. The series is not centered at 0. Where is it centered? 1. So I don't have powers of x, I have powers of x minus 1. Yeah, so everywhere I have an x minus 1. Not a huge mistake, but it's enough of one that we should correct it right now. This should be an x minus 1 right there. This should have been an x minus 1 right there. So this right here will be an x minus 1 in the absolute value. So remember how to read these. The center is that red 1, and the radius is also a 1. So that means an endpoint on one side is 0, endpoint on the other side is 2. Yeah. So our interval partially completed. So right now we don't know what's going on at 0. Here's 2 over there. 1 is our center in the middle. We do know that in between we have absolute convergence, right? That means the absolute value converges. But we don't know what's happening at the endpoints. So we'll come back to that later. Well, that was kind of fun. Some other complications about this sucker right here. I can't put this in a summation formula because this thing right here ain't exactly a factorial. There's no button for that on the calculator or in GeoGebra or in Wolfram Alpha. Okay, I don't think if I typed 1 times 3 times 5 ... 2n minus 1 that Wolfram Alpha would get the gist, but it might. It's pretty smart. I'll try that later too. Make a note. You can mess around by, oh yeah, oh my gosh. You probably can. Well, there actually is a notation for odd factorials, but most computer systems don't have them. I could write a little script that does it, but most systems don't have that built into them. But that just gave me an idea. One thing we could do to this, and I don't want to do it too long because I want to show Taylor's remainder theorem before we go, is I could throw in here a 2 times 4 times 6 all the way down, which basically turns the top into a factorial. Now I can't just multiply 2 times 4 times 6 in, that's kind of illegal. So what I have to do in the bottom, I would have to multiply a 2 times 4 times 6 all the way up to whatever the last one I need is. I guess the last one would be 2n minus 2. But I can factor a 2 out of every one of those guys, which is going to give me a 2 to some power times 1 times 2 times 3 all the way up to n minus 1, which is n minus 1 factorial. So it turns out we could rewrite this in terms of factorials and powers of 2. So I'll come back, I'll report back to you on that tomorrow. Yeah, Wolfram Alpha, check endpoints, and rewrite formula. Okay, rewrite. All right, it's in my to-do list. All right, so let's talk about Taylor series in general and the remainder theorem, which is pretty awesome. Let's see, Taylor series remainders. So to talk about Taylor series remainders, I have to remind you all about Taylor polynomials. And all a Taylor polynomial is a Taylor series, but you stop. You don't go forever, right? Series implies you go forever. Taylor polynomial means you stop at some value of n. So for example, for the square root of x, it's approximately equal to its Taylor polynomial to the, let's say, third power, which would be 1 plus 1/2 x minus 1 minus 1/2 x minus 1 squared plus, I think it was 1/8 x minus 1 cubed. And let me double check that I got that correct. No, it's 1, 1/2, negative 1/8, 1/16. Aha. Okay, so this is a 1/8 there, and this is a 16th over here. So question, actually, just a side note, does the series alternate strictly? If you ignore the first term, it does, right? And it turns out as long as it infinitely many, the tail strictly alternates, that's good enough. So actually, in a case like this, for some values of x, for which x minus 1 is positive, the alternating series theorem applies to this, which is kind of cool. But for the values of x for which this is negative, that messes up the strictly alternating, and then the alternating series theorem doesn't apply. Okay, so then I would have to use something else like the integral test to talk about remainders. And so kind of related to the integral test is Taylor's idea about remainders. And Taylor, when he developed this, did have an idea about the remainders, but it was another guy, which one was it, that actually came up with the better definition of it. Oh, I can't think of his name right now. It'll come to me. So here's the Taylor polynomial. Now, with any Taylor polynomial is a remainder polynomial. So the third remainder polynomial picks up after this one ends. And so for us, let's see, what did we calculate? The next one was at the 5 out of 128. Yeah. So the third remainder would be negative 5 over 128 times x minus 1 to the power 4 plus, let's see, did we calculate the fifth one? We didn't calculate it. So it's 3 times 5 times 7, 2 to the 5th, 5 factorial. So it's 3 times 5 times 7, 2 to the 5th, 5 factorial. And this reduces a bit, but you get the point. And what's the problem with the remainder series? It goes on forever, right? So what we want to try and do is somehow estimate for some values of x Now, this is assuming that my original function, square root of x, is infinitely differentiable. Okay, if at some point it stops being differentiable, I have a problem because then I can't generate coefficients, in which case I really don't have a Taylor series. But I think we could see from our work here that this is going to be infinitely differentiable. We'll be able to keep doing that over and over. Now, we're centered at 1, which is good, because if I tried to plug in a 0 here, the negative exponent means it's undefined. So the series, the coefficients are undefined at x equals 0. That doesn't mean the series is, but it might be. That's something we still have to check. So what this, man, it's bugging me. I can't come up with that guy's name. Oh, it'll hit me later. So what this other mathematician discovered was that, and it's kind of related to the intermediate value theorem, that there is some special value we're going to call z that's in our interval. And right now our interval is from 0 to 2. Such that the infinite remainder Am I stating this right? I don't think I'm stating this right, is equal to the fourth coefficient. Oh no, it's less than. I think that's the way it goes right there. Less than or equal to the fourth coefficient evaluated at this special value in that interval z. You got to take the 1 away from it to the fourth power. Now, finding that number is a problem, right? That's generally not that easy to do. And so what we rely on instead is we take a look at the nth derivative of the function. So we would look at the fourth derivative of our function. And what we would try to find is, looking at the graph of the fourth derivative in our interval, we would try and find some maximum value. And that's basically what this is saying right there. And if we can come up with some maximum values, what they call an upper bound, then kind of like the alternating series test, and this is kind of based on the alternating series test, kind of related to well, it is related to the alternating series test. It's related to the mean value theorem, the intermediate value theorem, and what else? The integral test. It's kind of complicated, but what we can do then is say, hey, if I stop here for a given group of x values, I know my series has to be less than a certain amount. And so we have to look at that fourth derivative. Now, we calculated that fourth derivative back here. That's this guy right there. So, and all of this has to be an absolute value. So basically, I need to consider, oops, that's in the wrong spot. Let's move you there, move you there. All right, new page. So the fourth derivative of our function was equal to negative 3 times 5 over 2 to the fourth times 4 factorial. Now I know we cleaned that up a little bit. Times x to the negative 7 halves. And so what we need to do is we need to take a look at that graph and see if we can find a max in the interval from 0 to 2. So sometimes what you need to do that is you need to take the next derivative, set it equal to 0, and see what you find. And whenever you're looking for a max on an interval, one problem here we have is an open interval, which means there's no guarantee of finding a max. Only on closed intervals is there a guarantee of finding a max. So inside that open interval, we're hoping to find one. and so often what I do here, since we have so much technology, is just look at the graph and see what we see. And turn you guys off. So we want 3 times 5 divided by 2 raised to the fourth times 4 factorial times x raised to the power negative 7 over 2. All right, and we're curious about that thing from 0 to 2. And of course, it is asymptotic, which is a problem. So this is one of those cases where we are not guaranteed a max. So what we can do is we can cut our losses short and say, well, zoom out a little. Since it drops to the right and increases to the left, I could say, well, let's just look at x values within a half of 1. So like negative 1/2 to 1.5. So x equals 0.5. So we'd be just curious about that intersection right there. And let's see, GeoGebra will happily find that for us if I just point and click. And so GeoGebra says that happens when y is about 0.44-ish. So if we bump that up to say 0.45, then we have a maximum in the interval from 1/2 to 1.5. So we can here say restrict the interval. And we have to do that because 0 is a problem. There's an asymptote. (0.5 to 1.5, right? We're still centering it at 1. Usually want to stay with the same center. And in that interval, we found that the fourth derivative is less than or equal to 0.45. That gives us enough wiggle room. So with that in mind, what I get for the remainder theorem is that the error in approximation, which is that remainder, has to be less than or equal to 0.45 over n factorial times x minus 1 to the n. And let's say I need absolute value around that too, because depending on x, this might be positive or negative, and depending on n. Right, so that's our max that goes right in there. So you might ask, what happened to all of this stuff right there? How come that's not in there? Well, we took all of that into consideration when we found the max because that was part of my function. So that's hidden in this 0.45. Okay. And so with this, we can then say, all right, in this interval, we know our function is this accurate. Now, this is mainly toward the edges that we lose accuracy. The closer we are to the center, the more accurate we're going to be. So we'll play around with this idea a little bit more tomorrow. We'll test some functions and the accuracy in that interval to see if Taylor's remainder theorem does put us close enough for any particular boundary. The hard thing about this is if somebody says, hey, I need you to be within a millionth, then we have to fiddle around with how far out we need to go to get the accuracy. If we know we just want to go out 4 terms, then we can calculate the accuracy in any given interval. Okay, but the reverse problem is a little tougher. Somebody gives us an arbitrary accuracy, we then need to figure out how far out to go on our polynomial. Okay, all right, that's it for now. It's a beautiful day. You guys got other stuff to do.